For centuries, coal has been one of the cheapest, most reliable and safest forms of energy, providing heat and power to communities all around the world. Coal is also an essential ingredient in the manufacturing and construction industry, where the coke produced from black coal is used to convert iron ore to steel. Australia has the fourth largest share of coal reserves in the world, and coal mining in this country dates back as far as the 1830s.
Today, coal is one of Australia's leading export earners, contributing significantly to the economy. Continuous improvement in mining technology and ongoing funding of research from organisations such as ACARP ensure that Australia remains one of the safest, reliable and most efficient producers of high-quality thermal and metallurgical coal for both domestic and international markets. Coal may be mined using both underground or open-cut methods. This series of videos focuses on the geotechnical hazards associated with open-cut mining methods, with an emphasis on operational hazard identification and controls, mining practices, processes and systems, as well as equipment capabilities.
Where coal is located close to the surface, open-cut mining methods are typically favoured. Waste rock is removed by drag lines, electric rope shovels, excavators, or a combination of these, and transported to dumps by large electric or diesel-powered trucks. Surface miners and in-pit crushers and conveyors have more recently been utilised in open-cut coal mines to mine both waste and coal. The mining process typically begins with an initial excavation, called a box cut, and then progresses down dip in a series of strips, with the coal closest to the surface extracted first. Pit geometry is dictated by equipment capabilities, such as dragline reach or shovel height, the location of target coal seams, and geotechnical constraints to achieve a safe design. An active strip is generally bounded by a high wall representative of the direction of mining, a low wall comprising waste material dumped on sections of mined out or uneconomical ground, and end walls, which are generally perpendicular to high walls and represent the lateral extents of the strip being mined. High walls and end walls are usually hard walls, that is, their exposed face is excavated through undisturbed rock. They may also be fully or partially blasted to form what is called a soft wall or buffer wall. The purpose of this is to disrupt any persistent structure behind the high wall or end wall face with the intent of increasing slope stability. Benches may also be incorporated into both excavated and dumped slopes to increase slope stability. As mining progresses, the waste rock is generally required to be drilled and blasted so equipment can move material as efficiently as possible. Sometimes the waste rock is weak enough that the material may be free dug and drilling and blasting may not be required. Blasting may occur in blocks or fired for an entire strip. Scheduling requirements drive the blasting sequence. This is to limit equipment downtime and ensure continuous access to coal to meet shipping requirements. Once the target coal seam is uncovered, the coal is generally extracted with excavators, dozers or loaders. Depending on the hardness of the coal, blasting or ripping may be required to enable handling of the coal from its in situ position so that it can be transported to the coal preparation plant. This process continues until coal mining is no longer economically viable. Open-cut coal mines are projected to get deeper and dumps higher as mining continues into the future.
Geotechnical hazards can occur at any scale of excavation or dump. It is therefore important to familiarise yourself with the geotechnical hazards outlined in the following sections. There are many types of principal hazards in open-cut coal mining. Principal hazards are those which have the potential to cause multiple fatalities, and geotechnical failure is classified as a principal hazard.
This series of videos focuses on the risks associated with geotechnical failure and will include descriptions of the risks associated with isolated rockfall events through to large-scale multi-bench failures in both excavated and dumped slopes. The following sections discuss the warning signs and the controls commonly implemented to minimise risks relating to geotechnical failures. Before discussing failure modes and warning signs, it is important to define some commonly used geological terms in an open-cut coal mine. Defects. This is an overarching term used to describe any break or fracture in the rock, such as a joint, fault, bedding plane, or intrusion. Joints are fractures in the rock along which there has been little or no movement. Faults are fractures along which adjacent blocks of rock have moved either vertically and/or horizontally. The zone around the fault may be further weakened by soft clay material referred to as fault gouge. Bedding planes are contact surfaces which separate different rock types. Dikes and sills. Dikes and sills are types of intrusions of once molten rock through overlying sedimentary rock. Depending on their composition, they may result in local weak zones. Geotechnical failure of intact rock or dumped material can be a result of one or a combination of geological, hydrogeological, or mining conditions. Geological conditions contributing to failure include the frequency, orientation, and length of any structural defects. Changes in rock type, for example, from competent sandstone to weak mudstone or coal. Persistent dikes or sills. Extensive zones of highly weathered rock or local rolling of generally horizontal strata, and weak floor conditions, particularly at the base of low walls or dumps. Hydrogeological conditions contributing to failure include an increase in water pressure as a result of groundwater flow or blockage of groundwater flow behind the slope face, and ponding of water on the crest or at the toe of an excavated or dumped slope. Mining conditions or practices contributing to failure include dump tip heads formed from highly weathered or saturated waste material. Dump tip heads dipping towards the dump crest, where the additional weight applied to the tip head crest when a truck reverses to dump its load can initiate a failure. Inadequate bench widths. Strip geometry, where strip configurations that contain inflection points or bull noses are more susceptible to failure than those that have a consistent orientation. Poor blasting and excavation practices that leave hang-up or jagged excavated faces, particularly around transition zones from soft walls to high walls. Loading conditions, such as waste material or equipment being positioned too close to the dump or high wall crest. Dumping of waste material into water or mud, leading to degradation of waste material strength. Dumping sandy or highly weathered material at the base of a dump. Drilling or tramming of equipment next to or in the vicinity of freshly dumped waste slopes, coal stockpiles or excavated slopes that exhibit a jagged face with loose rocks or blocks in the face. Vibrations can result in a rapid loss of cohesion of dumped slopes or coal stockpiles, or cause loose rocks to dislodge in rapid time, and deviating from the mine design without geotechnical review. For example, dumping or excavating past designated surveyed control limits, or oversteepening or undercutting design slope batter angles. The next section will discuss the main types of geotechnical failures that occur in open-cut coal mines. In excavated slopes, these include planar, wedge, toppling, and composite failures. In dumped material, these include active-passive wedge failures. Failures that may occur in both excavated and dumped slopes include circular failures and isolated rock fall failures. Planar failure. These types of failures occur where a block of rock slides along a single defect that dips and daylights in the excavated face. Wedge failure. Wedge failure occurs where two continuous planar defects intersect and daylight in the excavated face. Toppling failure. Toppling failure occurs when persistent defects dip steeply into the excavated slope and the blocks or columns formed topple out of the face. These failures generally have a weak layer at the base that the vertical blocks slide along. Composite failures. These are typically the most common type of failure in excavated coal mine slopes. Composite failures involve a combination of planar, wedge and toppling failure modes along persistent defects, and also some component of rock mass fracturing and failure. Typical composite failures are vertically to subvertically bound by structural defects and horizontally bound by a weak, generally carbonaceous layer. Such failures occur at both the individual bench scale or as a failure of the overall pit slope. Active-passive wedge failures. These type of failures occur in dumped slopes, particularly where the dump is formed on a weak and/or steeply dipping floor. Circular failures. Circular failures occur in highly weathered, soil-like or dumped material that contains little to no large rock fragments. Circular failures may be deep-seated or may occur near the surface, where they are referred to as skin slippage failures. Circular failures typically result from an excavated or dumped slope that is greater than the angle of repose through undercutting or over-steepening mining practices. Isolated rock falls. These are failures in which individual rocks fall out of a dumped or excavated slope face. Isolated rock falls can be just as hazardous as failures involving a whole slope face. They generally occur after heavy rain events, where poor separation of dumped material has occurred, or where blasting has been poorly executed and the face not adequately scaled for loose rocks at the time of mining.
Geotechnical failures rarely occur without prior warning signs. Regular inspections and familiarity with the work environment are therefore key to identifying changes in conditions which may indicate impending slope failure. Every coal mine worker is responsible for being familiar with their working environment and reporting hazards. The following section describes common warning signs that may lead to slope failures.
As the factors that drive failure are different for excavated slopes and dumped slopes, the warning signs of these failures will be different. While there will be some overlap, there will be different warning signs for high wall, end wall and soft wall failures. There will also be similarities and differences between the warning signs for dumped slopes involving wet rejects, dragline spoil and truck and shovel waste.
Slope failures also occur in coal stockpiles. You must be familiar with the warning signs for all types of excavated and dumped slopes. Warning signs include isolated rock falls or loose material at the toe of excavated and dumped slopes. Lipping, which refers to the horizontal movement of strata in an excavated face along defect or weak planes. Crushing or spalling of coal representative of local concentrations of high stress, and floor cracking or heaving. A sudden increase or decrease in water seepage from a dumped or excavated slope face observed either visually or measured by instrumentation such as piezometers or standpipes. Water seepage from coal stockpiles is particularly critical for identifying the potential of failure in this type of dumped slope. Hang up or cling on material in front of pre-split barrels or above previously failed sections of slope. Visible undercutting or over-steepening of an excavated or dumped slope. Undercutting is particularly critical for identifying the potential of failure in coal stockpiles. And cracking, slumping, bulging or heaving in the face behind crests or at the base of excavated or dumped slopes.
Once a geotechnical hazard has been identified, an inspection will be completed as per site requirements. Controls will then be put in place to effectively manage the hazard. Controls must be followed at all times. If you observe conditions to change from those documented in the site hazard report, notify your supervisor immediately.
Typical controls to manage geotechnical hazards using the hierarchy system include elimination controls, scaling or chaining of slope faces and crests to remove loose rocks, trim blasting to remove unstable ground, redesign or engineering controls, altering the blast design, such as changing from a hard wall to a soft wall. Installing temporary buttresses. Reviewing and redesigning the mine plan, such as incorporating additional benches into both excavated and dumped slopes. Only allowing equipment with falling object protection installed to work within the hazard zone. Separation or isolation controls. Controlling access at the crest or toe of the identified hazard by installing hard barriers. Restricting to single lane access past the hazard. Limiting equipment used in the hazard zone, such as allowing the excavator arm and bucket only inside the hazard zone, or modifying or restricting the dragline dig sequence to minimise exposure to the hazard. Regrading or re-establishing tip heads. Rectifying drainage conditions, including installing pumps and grading slopes away from the crest into a sump. Administration controls. Increasing the frequency of inspections, allowing only experienced operators within the hazard zone. Completing additional risk assessments for specific mining sequences, such as mining on retreat or backfilling after mining coal. Establishing monitoring controls, such as peg telltales, wireline extensometers, prisms, LiDAR or slope monitoring radars. Restricting operations to daylight hours only, or installing additional lighting. The number and nature of controls is governed by the consequence and likelihood of a slope failure occurring. Slope monitoring and implementation of standoff zones are two of the most commonly applied and effective controls if managed correctly. Slope monitoring is completed by one or more of the following methods: visual inspections, peg telltales, wireline extensometers, prism monitoring, laser scanners, drone surveys, LiDAR or slope monitoring radars. Monitoring devices can be used for either long-term, broad-scale detection of slope movement or targeted monitoring of a specific area of concern. Regardless of the monitoring device implemented, it is important to remember the following. Monitoring devices deployed should be able to measure the direction and magnitude of slope movement. Monitoring backsite devices need to be mounted on stable ground, otherwise false or misleading measurements can be recorded. Monitoring equipment needs to be regularly inspected and serviced to ensure it is operating as required. Trigger or alarm levels need to be predefined and should be set at levels specific to site conditions. Standoff distances can be applied at both the crests and toes of excavated or dumped slopes. Standoff zones are typically based on empirical charts, past performance of slopes with similar conditions, or modelling results from software simulating individual rockfalls or slope failures. The applied standoff distance should be appropriate for the type, size, likelihood and consequence of slope failure. Many sites have standard restriction zones that are applicable at all times. Increases or decreases to these standard restriction zones are then made on a case-by-case basis depending on the specific hazards present.
Good mine planning design is the best way to reduce risks from geotechnical hazards to acceptably low levels. There are statutory requirements, accepted industry standards, and company-specific procedures and criteria that must be followed. Every coal mine worker must understand their responsibilities under the site's procedures and take actions when necessary. If you're unsure of your responsibilities, ask your supervisor.
Mine sites must have in place processes and systems that outline roles, responsibilities and management plans to identify and control geotechnical risks. These may include standard work procedures, standard operating procedures, principal hazard management plans, and trigger action response plans, commonly referred to as TARPs, outlining the minimum actions and responses for normal and elevated risk states relating to geotechnical hazards. All slope designs should have an appropriate factor of safety or probability of failure. This value may vary depending on slope geometry, required lifespan of the slope, and the consequence of failure. All slope designs should be designed and reviewed by a suitably qualified and competent geotechnical engineer. Best practice is to have designs peer-reviewed by a similarly suitably qualified and experienced geotechnical engineer.
Open-cut coal mines are dynamic environments. Coal mine workers must be familiar with their work environment at all times. Always remember, rocks fall down, so look up and look around. If you see any of the warning signs, notify your supervisor, the open-cut examiner, or the geotechnical contact on site. Follow all instructions given by your supervisor and minimise your exposure time in delineated geotechnical hazard zones. Coal is a critical source of energy now and in the foreseeable future. Invest your energy in identifying and reporting the warning signs of slope failure to ensure safe production of this vital commodity.